So here we have another exam. Differential equations from fall 2023. I love the smell of a math exam in the morning. And so this is going to be fun. We have first and second order differential equations to explore, the basics, a lot of fun stuff. So let's get started. But of course, before we begin, don't forget, you need to put your name down, because if you don't, you won't get the credit. So we'll say solutions, and off we go. Number 1, find the explicit solution of the following initial value problem. We have x dy dx minus y is 2x squared e to the 2x. All right, what do we see? Well, one thing is we have this thing dy dx. Now remember, dy dx is just another way to say y prime. So this is the same as xy prime minus y is 2x squared e to the 2x. Now, why write it as y prime versus dy dx? It just depends on what you want to do with it. Sometimes it's easier to see when we have dy dx. For example, if we were inseparable or if we were in exact. Sometimes it's easier just to have the y prime, because one of the things is we've learned how to spot problems. You know, so when we're out in the wild, we're like, oh, I recognize that problem. So for us, what's our clue of what we need to do? Well, our clue is we see a single y and a single y prime, and that's it for the y's. So we say, oh, that means something. In particular, that means that this problem is linear. So we're going to use our technique of solving a linear differential equation. Now, the first thing we do when we're faced with a linear differential equation is we have to be careful. And by that, I mean, we look in front of the coefficient of y prime. And we say, okay, what is it? Well, it's x. And we're like, no, we don't want x. We want 1. So we should make it a 1. Okay, well, that's not so bad. We can do that. We have the technology. The technology, by the way, is also known as you divide. So we're going to divide everything by x. So we'll get y prime minus 1 over xy is equal to 2x e to the 2x. So remember, everything gets divided by x. And don't worry about this part yet. Don't start thinking like, oh, integration by parts, or oh, it's going to wait. Wait until you get to that, because there's still work to be done. Okay, now that we've gotten this part, we say, okay, we've got that 1. We're going to come and grab the coefficient of the y. And don't forget you need that minus sign. We're coming up with our integrating factor. So I like to use rho, but some people use mu. It's all right. It doesn't matter what you use. It just matters that you have the right technique. So you have e to the integral of this coefficient, minus 1 over x dx. Well, that would be e, and the integral of minus 1 over x is minus log x. And that's the same as using properties of logs. That's e to the log of x to the minus 1, which is 1 over x. And then e and log are inverse functions, so we have 1 over x. So that says our integrating factor is 1 over x. So what do we do with that? Well, the punchline is we're going to take this 1 over x and we're going to multiply the whole equation. Now, which one? Not that one, this one. The one where we had that coefficient. So which is to say, we're going to multiply all of this by 1 over x. All right, so what do we have now? Well, we have 1 over x, y prime, minus 1 over x squared y is equal to 2 e to the 2x, because everything got multiplied by 1 over x. And here is the magic of the technique. We know by design that this left-hand side is nice. It is the derivative of 1 over x, y. And you can even go and check this, right? You have the first times the root of the second. Then the root of the first, well, the root of 1 over x is minus 1 over x squared times the second. Okay, so the derivative of 1 over xy, well, that's 2e to the 2x. Now we're in our happy place, because the hard part for us was handling the y. But now that's inside a derivative, and that's an easy thing to handle, because when you integrate a derivative, you get the function back. So 1 over x times y is, well, now we have to integrate this part. And this is a nice integral. See, it looked like terrible. It looked a little less terrible, and now it's like, ah, or maybe I should say, ah, it's not so bad. So the integral, the 2 comes out, and then we'll have e to the 2x. But then we say, oh, we have to compensate for that 2 upstairs, so we divide by 2. And then don't forget a plus c. Okay, or we can, of course, cancel the 2's and multiply by x. We have that y is x e to the 2x plus c times x. Good. Now, we've just found the general form. Are we done? No. Are we closer? Yes, we are very close. The only thing that we haven't taken into account yet are initial condition. So we need to say, well, all right, how do we handle that initial condition, y of 1 equals 0? Well, we plug it in. Now be careful here, because oftentimes we plug 0 in for x, but it's not 0 for x, it's 0 for y. X is 1. So this is telling us here, we'll just write it again, that when x equals 1, y equals 0. All right, so when we plug that in, we have, well, 0, because y is 0, is equal to 1 times e to the 2. That's e to the 2 plus c. You say, oh, all right. Well, that tells us that c is minus e squared. All right, so putting that in, we just replace c by minus e squared. We get y is equal to x e to the 2x minus e squared times x. So this x is not in the exponent, it's downstairs. And we're done. That's it. Beautiful answer. You know, the initial condition is a little bit tricky, and making sure you recognize linear, okay? But not too bad. Not too bad. It's a nice way to start a test. All right, well, on to the next one. Number 2. Consider the following differential equation. 3x squared y plus cosine of x dx plus x cubed plus 3y squared dy equals 0. Find the general form for implicit solutions to this exact equation, and then include justification that this is an exact equation in your answer. Now, of course, we might start to wonder, well, what kind of problem is this? But there's a clue here, and the clue is it tells us it's exact. So, you know, that's fun. And so now that we know it's exact, we're like, oh, exact. So we know what to do. We know exactly how to begin. Now, the idea of exact is that we really have 2 pieces here, and these are giving us 2 snapshots of our function. And what we want to do is somehow combine these snapshots together to build up a bigger function, which forms the basis of the solution. So how do you go about doing it? Well, the answer is you integrate each piece, and then you put them together. So we're going to integrate, so we're going to integrate the first part. Well, all right, so integral 3x squared y plus cosine of x dx. Notice the dx here. That says we're going to treat x as the thing which can vary, and if you're not x, we treat you like a constant. So for example, y, we're going to treat that like a constant. So when we have an expression like 3x squared y, well, it's like, oh, there's like a number, integral 3x squared, well, that's x cubed. So x cubed y, integral of cosine is positive sine. Yeah, the sine and cosine, they have that sneaky, like, oh, it's positive. You got to be careful, but that's all right. We're patient. And then, of course, there's a constant. But now, it's not a constant number, it's a constant function. Just anything which is constant with respect to x. Since y is constant with respect to x, it's really a function of y. All right, and then we're going to do the same thing with the other part. So we're going to say, all right, the integral of x cubed plus 3y squared dy. Well, again, the dy says we're integrating with respect to y. Y is a variable, x is a constant. So this is a constant right now. And the integral of a constant, well, it's a constant times the variable, so x cubed y. Integral of 3y squared with respect to y, y cubed, and then again, some constant function of x. All right, so again, we're seeing two snapshots of a function. And we have to say, all right, can we put them together? Now this is where you can test for exact. And the test for exact at this stage, if you're doing it here, is you say, oh, compare. The parts with both x and y match up. And if that's true, then the conclusion is we're exact. So this is one way to do the justification. We'll point out a second way at the end. But now we've justified that it's exact. In essence, you could argue finding a solution is a way to show it's exact, but then you have to say, well, why did the solution work? Okay, but now we're ready to put things together. So we have the parts which agree. So that's the overlap parts. So we'll write that. That's x cubed y. Okay, overlap. Then we have parts with only x. Now that comes from the first integral, and that's the sine of x. So plus sine of x. And again, this is the only x part. And then we say, well, parts with only y. That comes from the second integral. That's the y cubed. And this is our function, which I've been saying. We have two snapshots of a function. That's the function. That's not the answer, because the answer needs to have something equals something. And so this should equal something. Well, what? Well, we're looking for the general form. And so we need a constant, and this is where the constant comes into play. And we're done. That's it. That's the answer. So exact problems are actually really fun once you know it's exact. And here they told us it's exact. So it made it really, really fun. We didn't have to stress too much about it. But all right, well, oh, I said there was a second way. Let's talk about that really quickly, because I want to make sure for people who are like, well, wait, what's the other way? Well, the other way to check that it's exact is, suppose we call this m, and we call this n. So m is 3x squared y plus cosine x, n is x cubed plus 3y squared. So our other exact test works in the following way. Namely, what you do is you say, what is m sub y, and does it equal n sub x? All right, so come up here, take the derivative with respect to y. That says we're treating x like a constant, so that cosine x goes away. 3x squared is a constant, derivative of y is 1. So we say, okay, well, that's 3x squared. Over here, now we're taking the derivative of n with respect to x. Y is a constant, so that goes away. Derivative of x cubed is 3x squared. And they do indeed match, and so this says, aha, exact. So that's the other way to do it. So which one is the right way? That's the wrong thinking. It's not that one way is right and one way is wrong. It's just a matter of both are right, and it's a preference. I prefer to sort of do it during the process of solving, because it makes me feel like I don't have any redundancies. Whichever way you want to do it your way. As the song says, you'll do it your way. All right, on to the next problem. Number 3. For the autonomous differential equation, y prime is equal to y squared minus 3y plus 2 times y squared plus 3y minus 4, find and classify all the critical points as either stable, unstable, or semi-stable? Include a phase diagram in your answer. Well, what do we have? Now, autonomous just says y prime is a function of y. The good news is we don't have to solve. Woohoo! We do have to do something. So what's going on? Well, if you sort of put on your Calc 1 hat, we're looking for critical points. And you say, well, critical points, that's where the derivative is 0, right? Right! So what we're really saying is, okay, when does this equal 0? So let's look at that. Well, we have y squared minus 3y plus 2 times y squared plus 3y minus 4. Now, if this equals 0, that really says, well, one of these has to be 0. So we say, okay, well, is there another way we can write y squared minus 3y plus 2? Does it factor? It does. So this is one, not too hard to check. Y minus 1, y minus 2, right? You can check it, right? Y squared minus 2y minus y is minus 3y and plus 2. Well, that was nice. How about this one? Does it factor? We need two things that multiply to give minus 4, but add to give 3. Well, what about maybe y plus 4 and y minus 1? Let's check. Y squared, okay, minus y plus 4y is 3y and minus 4. Oh, okay. So actually, what's going on here is if we rewrite this, this is the same as y plus 4, y minus 1 squared, y minus 2 equals 0. So our original differential equation could have been written in a different way. Well, makes you wonder, why didn't they write that from the start? I don't know. They probably just wanted us to have some practice factoring. And they factored that into their problem writing, I guess. Okay, so wonderful. So now we know the critical points. Well, we say, well, there's a negative 4, there's a plus 1, and there's a plus 2. All right, so what comes next? Well, we found, so great. We have to classify. Well, for classifying, I really like phase diagrams, and we have to have a phase diagram in our answer anyway, so let's do that. So we draw a line, and we mark the points. So we have minus 4, plus 1, plus 2. Now, what we want to do is say, what's the sign? Well, all right. So we're going to go through at each interval and ask for the sign. So pick a number bigger than 2, like 1,000,000, or 3, just something bigger than 2. All right, 3. 3 plus 4 is positive. 3 minus 1 squared is positive. 3 minus 2 is positive. Everything's positive, so the derivative is positive. Between 1 and 2, well, 1.5, let's say, 3 halves. 3 halves plus 4 is positive. 3 halves minus 1 squared is positive. 3 halves minus 2, negative. Okay, so now we're negative. Between minus 4 and 1, 0. Classic 0. 4, positive. Minus 1 squared, positive. Minus 2, negative. So the net, when you put them all together, is we're still negative. And something below negative 4, we can do negative 5. Negative 5 plus 4, negative. Negative 5 minus 1 squared, positive. In fact, really, as soon as you square it, it's positive. So this is always positive. Negative 5 minus 2 is negative. So negative, positive, negative. Put them all together, we're positive. All right, which means we're going up, going down, going down, going up. This, by the way, is our phase diagram, which is part of our answer. And now we can just go through and list. So negative 4, we're going in towards negative 4. So negative 4, stable. What about 1? Well, 1, we're going sort of in on one side, out on the other. So 1 is semi-stable. What about 2? Well, 2, we move away from 2. So 2 is unstable. So that's the classify. And there's our answer. Our phase diagram, our critical points, and our classification. Nice. Nice. Number 4. Consider a linear differential equation for x greater than 0 of the form x squared y double prime plus axy prime plus by equals 0, with to be determined parameters a and b. On a side note, this is called an Euler equation, but we'll get back to the problem. Also consider the two functions. Y1 is x cubed and y2 is x to the minus 1. Okay, determine a and b so that y1 and y2 are solutions of the above differential equation. Now there's actually a couple ways you can do it. If you're familiar with how Euler equations work, you can say, well, the Euler equations, the way you solve them is you turn it into a polynomial. It's a little bit more subtle than constant coefficients, but you can, and then you find the roots. So you can actually reverse engineer that. You say, look, we have the solutions, which means we have the roots, which means we can find the polynomial, which means we can get back to the original. But like I said, it's more subtle that way. A simpler way is to say, we know the solutions, plug them in, and say, well, what does that tell us about A and B? And that gives us, relationships, and then we use those relationships. So let's start with the x cubed. So plugging x cubed in, what do we have? Well, we have x squared. Now, the second derivative of x cubed. Well, the first derivative would be 3x squared, and then the derivative after that would be 6x. So we have x squared, and we have 6x plus ax. And now we say, okay, the first derivative, 3x squared. And then be the function, x cubed equals 0. Now notice that every term has an x cubed, right? X squared times x times x squared, x cubed. So we can divide out by the x cubed, and when we do that, we're going to get 6 plus 3a plus b equals 0. Okay, so now we know a relationship between a and b. Let's do the same thing, but now we'll do it with x to the minus 1. Now x to the minus 1 is going to be a little bit more fun. So we have x squared plus ax plus b. So I'll start here, x to the minus 1. What's the derivative of x to the minus 1? Minus 1 comes down, then you'll have minus 1 x to the minus 1 upstairs, so that's minus 1 x to the minus 2, minus x to minus 2. Take another derivative. Minus 2 comes down. Well, there's already a minus. With another minus 2 makes a plus 2. X to what power? Well, minus 2 minus 1 is minus 3. Well, x squared times x to minus 3 is x to minus 1. X times x minus 2 is x to minus 1. And then you have x to minus 1. And you kind of know that that's how Euler equations should work, that all the terms should have the same power of x. So if you didn't have that, you're like, whoops, mistakes were made, check derivatives. So moving the x to minus 1 out, what's left? Well, we have a plus 2 minus a and a plus b. And now we're like, oh, we have two equations, two unknowns. One of our favorite things that we're really good at, two equations, two unknowns, we're pros at this. So we say, okay, well, let's solve. So in particular, I'm going to do a little bit of rearranging first. 3a plus b equals minus 6, and minus a plus b equals minus 2. And I see that the b's will be pretty quick to cancel. So if we subtract, 3a subtract minus a makes 4a. b minus b makes 0. Minus 6 minus minus 2, well, that makes minus 4. Well, that says a is minus 1. Now that we know a, what can we do? Well, we'll plug it in. Well, we can plug it in here. So we have 2 minus minus 1 plus b equals 0. Well, 2 minus minus 1 is 3. 3 plus b equals 0, so we get b equals minus 3. And so we say, okay, well, that's A and that's B. And what do we need to do? Well, we need to determine A and B. And so we're done with part A. A equals -1, B equals -3. Woohoo! Yes! And the problem continues. Part B. Calculate the Wronskian. Okay, and the Wronskian y1, y2. So we have Wronskian x cubed x to the -1. So that's the 2 by 2 determinant. In the first row, we put the functions x cubed x to the -1. In the second, the derivatives. Derivative of x cubed, 3x squared. Derivative of x to the -1 minus x to the -2. It's actually these functions right here. All right, now taking your 2 by 2 determinant, and remember, how does that work? We're going to take our diagonal. So we have our diagonal going down, our diagonal going up. So we get x cubed times minus x to the -2. And then we're going to subtract 3x squared times x to the -1. Well, x cubed times x to the -2 would be x. So this becomes a minus x. And then here, what do we have? Well, x squared times x minus 1 is x, so that's a -3x. Minus x minus 3x makes -4x. So there's the Wronskian. Okay, good, good. Now, on to the next part. Part C. Are the solutions y1 and y2 linearly independent for x greater than 0? Use the Wronskian to justify your answer. Well, we know that the Wronskian of x cubed x to the -1 is -4x, which is not 0 for x greater than 0. And when the Wronskian is not 0, we're linearly independent. So, yes. So in particular, everything is good. So really the test is 0 versus non-zero, and life is good. Now, finally, part D. Write the general solution of the above differential equation. Now, it sounds like it's a lot of work, but we say, wait, we have two pieces. We know that these are solutions. We know that they're linearly independent. So it would be super if we could put them together. Indeed, it would be a superposition for us. Yep, so we have y is a times the first function plus b times the second. Done. That's it. Wow. I don't want to say that's it like it was trivial, but you know, work through the process. And one of the nice things about this problem is that most of the pieces were independent of each other. So even if you got part A wrong, you could still get B, C, D right. And so it's nice when they do that. So don't, say like, I can't get part A, let me give up. No. Never give up. Never surrender. All right, well, on to the next problem. Number 5. A spring mass damper system with no external force is set up with a mass, m equals 1, a damping constant, c equals 4, and a spring constant, k equals 20. Initially, the mass is at equilibrium, so that says it hasn't moved yet. x0 is 0, but there is a motion going on. So the velocity is 4. So it's at its resting position, but something is moving it. All right, great. So part A, part B. Part A, determine the equation for x of t. So in other words, we want to say, what's the motion that this is experiencing? Well, this helps to remember how do springs work. You have your mx double prime. We can think of this mass times acceleration plus cx prime. This takes into account your damper. And then plus kx. That's your Hooke's law, which takes into account your spring, equals 0. So I say, all right, we know our equation. Do we know m, c, and k? Yeah, we do. How do we know it? They're given to us. And so we'll just mark that so we don't make any mistakes. There we go. Now we have x double prime plus 4x prime plus 20x equals 0. All right, we try to factor it. We try harder. We don't succeed, but that's all right. Well, actually, I shouldn't say we try to factor it yet, right? We got to first turn into a polynomial. I got ahead of myself. Okay, r squared plus 4r plus 20 equals 0. Now we try to factor it. Try harder. But we don't give up. We say, well, okay, if we can't factor it, no worries. We can use quadratic formula. We can even do some completing the square. We'll go ahead and do the quadratic formula. So negative b plus minus square root b squared minus 4ac all over 2a. So that makes negative 2 plus minus. Now here we have 16 subtract 80. Now that might sound hard. Think of it the other way around. 80 subtract 16 is a little bit easier to do. That's 64. But now flip it back. And so we have a square root of negative 64 over 2. We've already divided the 2 into the 4. Now square root of negative 64, well, the square root of 64 is 8. And then square root of a negative gets an I. So what do we have? This is negative 2 plus or minus 8i over 2. So that's negative 2 plus minus 4i. All right. Good. Now, what does this tell us? Well, complex roots says you're going to have sines and cosines. Not too surprising with springs. With springs, you kind of anticipate that there will be some sines and cosines involved because springs tend to look like sines and cosines as they go up and down. And so, remember, the complex part, that's what goes into the sine and the cosine. The real part, that's what goes into the exponential function. So, we know that x looks like some constant e to the minus 2t cosine 4t plus some constant b e to the minus 2t sine of 4t. Now our goal is to say, what can we say about a and b? Well, let's start with this x of 0 equals 0. When I see zeros, the more zeros I see, the happier I am, because zeros are our friend. We like zeros. So let's plug it in. We have that x of 0 is 0. Well, here we have a. E to the 0 is 1. Cosine of 0 is 1. That makes it a. Then we have b. E to the 0 is 1. Sine of 0 is 0. So we have 0 equals a, which we can solve for a. That tells us that a equals 0. Yeah, it's the same equation. Okay, so now we can update and say, oh, actually our solution looks like some constant e to the minus 2t sine of 4t. Okay, great. Well, now we want to do our x prime. Well, to get to there, we need to find x prime. So let's do that. We'll say that x prime, well, we'll have the derivative of the first, derivative of e to the minus 2t, the minus 2 comes down, minus 2, b e to the minus 2t sine of 4t. Then when we take the derivative of sine, we'll get cosine, the 4 comes out. So we're going to have a plus 4b e to the minus 2t cosine of 4t. Now, plugging in 0, x prime of 0 is 4, because it says it right there. Okay, we have 2b e to the 0, 1, sine of 0, 0. So that is not to be. 4b e to the 0, 1, cosine 0, 1. So that's 4b. So you say, oh, there we go. B has to equal 1. So what does that tell us? It tells us that x is e to the minus 2t sine of 4t, because we plug b equals 1. And there's the motion of the spring. It's surprisingly nice. Okay, well, wonderful, wonderful. All right. Well, that was part A. This one also has a part B. What does that say? Determine the time t greater than 0 the spring reaches its maximum displacement. So in other words, you have the spring going up and down, but you'll notice that there's this exponential function. So what's going to happen is that as the spring goes up and down, it's going to start to, over time, shrink. I was rapidly shrinking, but you can say, okay, so since it's going to shrink over time, when does it get as far away from zero? Well, the answer is the first time it goes up. Because after that, every time it goes, it gets smaller and smaller. So we say, okay, so you may assume this is the smallest time t greater than 0, for which, of course, x prime of t is 0. Because maximum displacement is as far off as possible, so we're trying to optimize that. So it's, how do you do optimization? Take the derivative, set it equal to 0. So it says, okay, it's kind of telling us what to do. Take the derivative, set it equal to 0, solve for t. And then write your answer in the form A arctangent B for appropriate values of A and B. Arctangent. I was worried that this exam wasn't going to have an arctangent, but thank goodness. In problem 5, we were saved at the last moment. Well, not quite the last moment. There's still problem 6. So, but all right, back to work. So we can say, well, what is x prime? Well, we can take it here. It's really the same as we have up here, right? Because we know b equals 1. So it's minus 2 e to the minus 2t sine of 4t and plus 4 e to the minus 2t cosine of 4t. Now we set this equal to 0 because we're trying to optimize. Both terms have an e to the minus 2t. E to the minus 2t can't be 0. So what we can do is we can divide out. So I say, oh, great, 2. So we have minus 2 sine 4t plus 4 cosine 4t equals 0. Or you could rearrange this and say 2 sine of 4t. When does this equal 4 cosine 4t? Now, if we think about this, we're heading for arctangent. Well, how to get to arctangent? You can divide. And if I divide the cosine, divide the 2, that's the same as tangent of 4t equals 2. We're almost there. So we are looking for the value of time t where tangent of 4t is 2. What can we do? Well, take the arctangent and take the arctangent of both sides. 4t is equal to arctangent of 2, and then divide, and we'll get t equals 1/4 arctangent of 2. And so that's our time. And it has the right form, right? A arctangent b, so here a is 1/4, b is 2. So t equals 1/4 arctangent 2. Lovely problem, lovely problem. And that's number 5. One more to go. Number 6, our final problem. Find the general form for solutions to y double prime minus 5y prime plus 6y is equal to 50 sine 4x. Now, there's a couple of things to spot. First off, this side has something. So that tells us non-homogeneous. All right, non-homogeneous, that puts us into the category of undetermined coefficients or variation parameters. Which one are we at? Well, we look on the other side. Say, let's look at this part. Y double prime minus 5y prime plus 6y. What does it look like? Constant coefficients. Ooh, that's promising. And then we come back and say, well, sine, that's something that can come out of a constant coefficient ODE. And say, perfect. So that says both options are on the menu, right? We can do undetermined coefficients or variation of parameters. But here's the thing. We love ourselves. And then you might say, well, what does that mean? Well, that says we care about ourselves. We want to choose the option which is most likely to succeed. And not that both will, that either would fail. Most likely to succeed here means least amount of errors coming out. And between the two, undetermined coefficients will win. The thing that happens with variation of parameters, I'm just going to mention this, is you end up getting into integrals where you have to do integration by parts, and it can get dicey. And oftentimes you'll have things which, unless you remember how to do integration by parts, and this is one of those cases where you'd have to do integration by parts twice and rearrange, and you're like, you don't want to go that route. Undetermined coefficients, here we go. So, how do we start? Well, we start like we always start a problem like this, namely, we want to solve the homogeneous part. So, we're going to find our YC. So we do that by, we set y double prime minus 5y prime plus 6y equals 0. Turn it into a polynomial problem. And we say, they gave us something which factors. Well, of course, because your instructors are nice people. They care about you. They want you to succeed. So our roots are 2 and 3, which says that our homogeneous part looks like something ae to the 2x, be to the 3x. All right, we'll put that aside for now, and we're ready to go into the next part, which is find yp. Now, to find yp, the first thing is we have to say, well, in undetermined coefficients, we know what yp more or less looks like. How do we know that? Well, we start making a list. And we say, okay, look at this part and write down the functions. In this case, there's only one function. We have sine of 4x. And then we start going through our checklist. We say, okay, we have a sine of 4x. Is there any x's out in front of any of the terms? No. Good. We have a sine. Are there any times when we have a sine missing a cosine or a cosine missing a sine? Because they always come in pairs. Yes, we are missing. So we have to add the cosine 4x. That has to be part of our form. And then the third thing, okay, so we check powers of x, sine, cosines, and pairs. The last and third thing to check is, do any of the functions on our list that we've just put together match any of the functions that were part of our homogeneous solution? No. So we're like, phew. If they had, we'd bump. We don't have to. So these are going to form our particular solution, namely y sub p looks like some constant to be determined sine 4x plus some constant to be determined cosine 4x. Now this is not yp yet. Yp is particular, which means there's one solution. This looks like a whole range of solutions. So what we have to do is say, what are the right choices for C and D? Not every choice for C and D will produce a valid answer. In fact, only one choice for C and D will. That's why we call it undetermined, because we have to determine them. Now, how do we determine that? Well, we're going to plug this back into the differential equation and say, okay, what makes the right choice for C and D? So we get 50 sine 4x. So we're going to plug it in, which means we need the derivative and the second derivative. So we'll take yp prime, derivative of sine is cosine, 4 comes out, so 4c cosine 4x, derivative of cosine is negative sine, 4 comes out, so minus 4d sine of 4x, yp double prime, okay, derivative of cosine is negative sine, 4 comes out, so minus 16c cosine 4x, and derivative of sine is cosine, 4 comes out, minus 16d cosine 4x. All right, so plugging this in, we get the following. Okay, this is one of those things you just have to be patient. So we're going to do yp double prime minus 5yp plus 6, yp prime plus 6yp, well, equals, okay, so yp double prime, copy that down. And so we have minus 16c cosine 4x minus 16d cosine 4x minus 5 times yp prime. 4c, whoops, I just noticed something. You know, mistakes happen, but you start to say, wait, that doesn't seem right. Cosine, cosine, no, this should have been sine. Thank you for pointing that out. It's okay if you make small mistakes if you catch them. So keep looking for them. Keep looking for them. Because if things aren't working nicely, you should say, wait a second, did I make a silly mistake? Almost all mistakes are silly mistakes. And so once you realize that, you say, well, don't be so silly, and check yourself. As the great philosophers have said, you should check yourself before you wreck yourself. All right, so back to putting this in. 4c cosine 4x minus 4d sine of 4x, and then plus 6, and then y, c sine of 4x plus d cosine of 4x. Okay, now we have to gather, move into our hunter-gatherer mode. What do I mean by that? We're going to gather all the sines. What's the coefficients? We're going to gather all the cosines, and what's the coefficients of that? So all of that is equal to, okay, so let's start with the sines. We have minus 16c, and then here we have, don't forget about that minus 5, so minus 5 times minus 4d is plus 20d, then 6 times c. So there are our sine of 4x terms. And then, how about our cosines? Well, we have minus 16d, and then minus 20c, and then plus 6d, cosine 4x. Well, we can clean this up a little bit. Minus 16 plus 6, so that becomes minus 10c plus 20d sine of 4x, and minus 16 plus 6, minus 10d minus 20c cosine of 4x. All right, now what is this supposed to be equal to? This is supposed to be equal to 50 sine of 4x, but there's no cosine 4x. So that's all right, that just means 0 cosine 4x. So we did need the cosine 4x. If you don't include the cosine 4x, it won't work, because you'll be left with saying, okay, you'll get something here, but you'll end up with the cosine term. You'll say, wait a second, I wasn't supposed to have a cosine term. What happened? Well, we forgot to put it in to your initial guess. So now we say, oh, we really have two equations and two unknowns. Now notice here, 10, 20, 50, they're all multiples of 10. So we can simplify this expression and say this first equation says minus c plus 2d equals 5. Here, again, multiples of 10. And, well, we can divide out by even minus 10. And we'd have d plus 2c, so 2c plus d equals 0. And now we're like, wonderful. That's two equations, two unknowns, bread and butter. What? Our favorite thing. Well, I don't know if it's our favorite thing, but boy, we do it a lot. So we should be good at this. And so, all right, well, what can we do? Well, let's suppose we wanted to cancel the c's. Why not? If we multiplied the first equation by 2 and added, minus 2c plus 2c is 0. Then we have 4d plus d is 5d, and 10 plus 0 is 10. So we say, oh, that says that d is 2. Okay, come here. We have 2c plus 2 equals 0. So that says c is minus 1. So what's the punchline? Well, we now know the right values for c and d. And we had back here, takes a lot of space to do these problems, but we now know that c is minus 1 and d is positive 2. So we can conclude that our particular solution is minus sine of 4x plus 2 cosine 4x. Good, good. Now, where are we at? Let's recap what we've done. We found the complementary solution also you can think of it as a homogeneous solution, ae to the 2x plus be to 3x. Using undetermined coefficients, plugging it in to find those missing coefficients, we've determined that our particular solution is minus sine 4x plus 2 cosine 4x. What is it we have to find? Sometimes you've been working on the problem so long, you're like, wait, what was I looking for? So we go back and check, what does the original problem ask us to find? And it says, find the general form for solutions. How do you find that? Well, the answer is you combine the two. So in particular, we're after y is yc plus yp. So we just need to add these two, and that's the general form, and we're done. So let's just put them together. So we have that y looks like a e to the 2x plus b e to the 3x minus sine of 4x plus 2 cosine 4x. And that's the general solution. We filled out the page, but we stayed on it. And so there we go. Whew! That one was a good workout for us. But, you know, overall, I hope it wasn't too bad. And I hope you did well. And if you didn't, you still have more chances to learn and to get better. You know, this is a growth time for you. You're at a wonderful time in your life when you're learning, you're getting better, and you have lots of wonderful things ahead for you. Thank you for joining me. I hope to see you again. Bye.